Today, we're diving into a paper from 1980 from Geophysical Research Letters that really tackled a fundamental problem. How in the world do you study a tiny speck of dust from space after it's been flash fried by plunging through our atmosphere? It's a great story about cosmic dust and some really extreme heat.
So you gotta picture this. It's the 1970s, and scientists, pioneers like Don Brownlee, they start this incredible collection program. They're flying these high-altitude aircraft, basically trying to catch dust, almost impossibly small dust.
But of course, this isn't just any old dust you'd find in your house. No, this was being collected from the stratosphere. These are tiny particles just drifting down from the very edge of space itself, like little whispers from the cosmos.
And I can't overstate this. This was a huge deal. For the very first time, scientists had a completely new type of material from space that they could actually study in their labs on Earth.
So what exactly is this stuff? Well, they're called interplanetary dust particles, or IDPs for short. And when I say tiny, I mean it. Each one is about 10 micrometers across. That's thinner than a human hair. Now here's the really exciting part. The leading theory was that these were bits of debris from comets. That means we were basically getting a direct sample of our early solar system. This was totally different from any meteorite we'd ever seen before. A whole new class of extraterrestrial stuff.
Okay, so there's a problem, right? A major catch. Before these incredibly precious particles could be collected, they had to survive this absolutely brutal plunge through Earth's atmosphere.
And that plunge causes something called deceleration heating. Just imagine this tiny speck traveling at cosmic speeds and then, bam, it slams into our atmosphere. The friction with all those air molecules is so intense that the particle just flash heats in a few seconds.
And this created a massive dilemma for the researchers. Were they actually looking at a pristine messenger from deep space, a little time capsule? Or were they just studying a cooked artifact that had been totally changed by its crazy journey home?
You have to understand, this wasn't some minor detail. That intense heat could completely scramble the particle's chemistry, change its very structure. It could literally erase the cosmic history that the scientists were so desperate to read.
So what do? Well, to solve this mystery, they had to figure out just how hot these things were getting. So scientists like P. Frondorf, the author of this paper, they turned to physics and started building a model.
And the model showed the first key factor is the angle of entry. Think about it like skipping a stone on a lake. If it comes in at a really shallow angle, it's more of a glancing blow with the atmosphere. Less friction, less heat. But a steep entry, that's a direct hit, a total nosedive. And that generates a huge spike in temperature.
You know, one of the key scientists, Don Brownlee, had this fantastic way of putting it. He said that if the entry is gentle enough, one can get the Queen Mary in unmelted under the right conditions. It's just a perfect way to show how critical that entry angle really is.
Okay, so the second piece of the puzzle was the particle's own density. You've got these low-density particles, right? Think of them like fluffy cosmic dust bunnies. They don't heat up as much. But then you have the high-density ones, which are more like tiny, solid pebbles. They get way, way hotter because they absorb and hold on to that heat more effectively.
All right, so they've got the entry angle, they've got the particle density. By putting all this together, the model was finally ready to spit out some real numbers.
And this brings us to the million-dollar question, right? For a standard 10 micrometer particle, the kind they were actually finding, how hot did it really get during that fiery fall? And the model gave this amazingly clear answer. For a typical low-density, fluffy particle, the median peak temperature was around 550 degrees Celsius. But a high-density particle of the exact same size, it would rocket up to a blistering 800 degrees Celsius. I mean, wow, that's hot enough to bake a pizza in like a minute.
So what does that mean in practice? Well, it gave them this incredibly useful rule of thumb. It meant that if you went out and collected a bunch of these particles, you could pretty much bet that half of the fluffy ones had been heated past 550 C and half of the dense ones had gotten hotter than 800 C. This gave scientists a crucial statistical starting point.
So this is where it all comes together. This is where a physics model becomes an incredibly powerful tool for making new discoveries. The paper itself describes the model as a petrographic thermometer, which is just a brilliant term. You know, like a regular thermometer tells you your body's temperature, this model could tell you the peak temperature that a specific cosmic dust particle had survived.
So suddenly, the whole workflow for a scientist changed. Now they could collect a particle, take it to the lab, measure its size and density, and then plug those numbers into the model. And just like that, they'd get a good estimate of its peak temperature. And with that crucial bit of information, they could finally start to tell the difference between what was an original feature from a comet and what was just damage from the heat.
Because, you know, at the end of the day, this was never really about just temperature, was it? It was about creating a filter that let us see back in time. It finally let us read the original, uncooked stories that were written in these tiny grains of dust. Stories about comets, and about the very beginning of our solar system.
It's just amazing. This foundational work from 1980 paved the way for decades of research. And it really makes you wonder, as we keep getting better at collecting these tiny messengers from space, what other secrets are still out there, just waiting to be discovered, all hidden inside a single speck of dust?